Now let's see the second example. As always, I just prepared the code. Now I will copy the code and paste it here. Then we will see the code line by line. I just paste it here. This is the code for the second example. Until here. Code to implement PCA under spot XS multispectral image and display the result. However, before we begin, I would like to highlight two key points. First, in the previous example, we followed a basic step-by-step approach to understanding the principal component analysis as discussed in the introduction. Now, in this example, we will utilize the PCA class from the sklearn.decomposition library for a more practical implementation. Second, in this example, we will work with the satellite image dataset, specifically spot XS images. In real-world scenarios, image data is often used in various applications. So, I have chosen an image dataset as an example. The spot XS image consists of 3 spectral bands, namely 3 separate images. From this, we will generate an additional image, namely the normalized difference vegetation index, or so-called NDVI. As a result, we will now have 4 images, 3 original spot bands and the newly calculated NDVI image. Next, we will create an image dataset containing these 4 images. After that, we will apply the principal component analysis and extract the first 3 principal components. This transformation will retain the most significant information from all 4 images while eliminating redundant data. The goal of this example is to compress the information into fewer components while preserving meaningful data. Now, let's see the code line by line. Namely, in this example, we are going to use spot XS images because in the real-world scenarios, sometimes we encounter image data. Therefore, here in this example, I am using the spot XS image as an example. In the first step, I just imported necessary libraries, imported image class, numpy, pandas, sklearn.preprocessing, min, max scala, because in the following section, first we will calculate the normalized vegetation index. Its range is from -1 to +1. However, other spot bands, other spot images, ranges are from 0 to 255. Therefore, using this min-max scala, we are going to rescale the newly calculated NDVI image from the default -1 to +1 range to the new from 0 to 255. Therefore, I just imported this min-max scala. Later we will see this. Then imported the PCA class. In the previous example, we just used the linear algebraic equations and some other functions, related functions. We just calculated the PCA, namely principal component analysis, step by step. But here we are going to use this built-in sklearn decompositions PCA class. This is very convenient class. In the practical situation, always we use this because this is very convenient, and in the later we will see it. Then I just imported matplot library in order to display some data. Step 2, just load the spot XS full scala composite image. In the step 3, by using numpy's array function, we just converted the image into RGB arrays. Here, we just get the height and the width of the image because later we will use it for reshaping the result of the principal component analysis. Namely, we use this later for reshape PCA result. Step 4. Extract the original near-infrared and red spot bands or reflectance from the RGB array. Because now we have the RGB array, now we are extracting the near-infrared and the red bands. Because in order to calculate the normalized vegetation index, we need to use near-infrared and red informations, namely reflectances. Therefore, we just extract the near-infrared and the red reflectance or bands from the RGB array by using these two indices, namely 0 for the near-infrared and 2 for the red. Then we just changed it, we just cast it float, because in the original image they are 8-bit data, namely unsigned integer. Now we are changing it, we are casting it as float image. Okay, because we use it during the calculation. Step 4, we just calculate the normalized difference vegetation index by using the near-infrared and the red reflectances. In order to avoid a division by 0, I just added this very small number. As a result, the range of the resultant NDVI image will be in this range, namely from -1 to +1. Then in the step 6, because we get the NDVI image from this calculation, and this image's range is from -1 to +1. However, the range of the other images, namely other bands, are from 0 to 255. Therefore, in order to make them same range, we just need to rescale this newly created NDVI image. Namely, step 6, we are doing that. Initialize a scalar with a new range, namely from 0 to 255, and scale the NDVI image from the range. Namely, when we calculated it, its range is -1 to +1. Therefore, here, namely, initialize a scalar with the new range of 0 to 255 and scale the NDVI image from the range, from this range to the new range of from 0 to 255. Here we are using this min max scalar. In the previous lecture we have seen this. Therefore, this is the instance, namely we just pass this target range, namely feature range, and then we get this instance. By using this instances fit and transpose method, we just converted, we just get the scaled NDVI image. This is the scaled image, namely after we get this, we just converting it integer, because other bands are in integer format. Therefore, we just converting it as integer. In the step 7, now we have 4 images here. The first 3 was the bands of the spot XS image, then NDVI. Therefore, now we have 4 images or 4 features here. Therefore, by using these 4 features, we just created a dictionary, spot underscore dictionary, creating a dictionary object with the original spot XS bands along with the newly calculated NDVI image. The first key is the XS3 infrared, and we use the first index here in the RGB array. Second key is the XS1, namely green, and the third one red. The fourth one is the newly calculated NDVI. Now we have this spot dictionary. It has 4 features. By using this dictionary, in the step 8, we are creating a data frame, compute the correlations, and generate scatter plots between the features to gain insights into the new spot underscore data frame. We just created this spot underscore data frame, namely this is the data set. This data set includes 4 features. The first feature is infrared, second feature is green, third feature is red, and the fourth feature is NDVI. Namely, now this is our final data set. By using this data set, we are going to calculate the principal component. We have this data set in the data frame format. Therefore, very easily we can calculate the correlation coefficient between the features. Therefore, as a reference information, I just calculated the correlation coefficient between the features. Namely, we have 4 features here. Therefore, this is the spot underscore data frame underscore correlation coefficient. We will display it here as a reference information. Later we will see it. Then we also displaying the scatter plots between the features. Now let's put it here. This is very useful, as therefore by using that, namely by using scatter underscore matrix, and we are passing spot data frame here. We just calculated spot data frame, and this is the figure size. Then we are showing it. We will get 16 scatter plots. This is also a reference information. In the step 9, we know that there are 4 features in the spot underscore data frame, and we want to reduce them to 3 using the principal component analysis. Then we rescale the PCA result, namely result of the principal component analysis, to the range from 0 to 255, because it's image data. Therefore, if we change it into this range, and it's very good in terms of visualization. Therefore, we just need to rescale it, then reshape it to height, width, and this is the number of channels, because as a result we get a kind of numpy array. Therefore, in order to change it to image, and it's easy to display, therefore we reshape it just like this. Now let's do this. First, we just create the instance of the PCA class. This is the principal component class in the sklearn.preprocessor. Then here we are initiating it by using this and underscore components, because we are going to get the first 3 principal components. Therefore, we just pass this number of components, namely initialize the PCA with 3 output principal components. Now we have the instance of the principal component analysis here. Then by using its fit and transform function, we just calculating the principal components of the spot underscore data frame. We are passing the data set to the instance of the PCA, namely to the function of the fit underscore transform function of the principal component. This is the result we get. Actually, the result is numpy array. After we get the result, and then we rescale it, because it's image. Therefore, we need to rescale it. We just rescale it here, and then we just reshape it to one array, and then we just change it to integer. Then we just reshape it to this image shape. Namely, here first, by using this fit and transform, we are changing its range from 0 to 255, because this instance's range is from 0 to 255. Therefore, we just using this instance, transforming the data, the result of the principal component into this range. Okay, then we are reshaping it, and finally we get the x underscore PCA3 image. Namely, this is the scaled principal component result. By using this, we just reshape it. We just changing it to an image here. Namely, this is the final 3 image. Namely, first principal component image, second principal component image, and the third principal component image. Now, this is the final result. Okay, after we get the final result, then in the step 10, we are going to get the explained variance. Namely, how much information in the first principal component, we have how much information in the second principal component and the third principal component. Therefore, we just get this from this instance, namely instance of the PCA. We had this kind of information. This information is restored inside this instance. Therefore, we just get it here. Then, by using this, because we have here 3 elements, namely first, second, and third. Therefore, we just calculate the cumulative summation, then we get the cumulative variance. Later we will see. After that, in the step 11, we just displaying the original spot XS bandits NDBI image, and we are displaying the final principal component results. Therefore, in this section, we are displaying the results. The first, we are displaying the spot bandits and the calculated NDBI. Namely, we are creating here figure. Then we are creating subplotters. In the first grid, we are displaying the near infrared. Second grid displaying the green band. Third grid displaying the red band. In the fourth grid displaying the calculated NDBI. Then here we are displaying the principal components and the color composite image from the calculated principal components. Namely, we are getting three separate images. Namely, here this is the first principal component, second the principal component, third principal component. We are displaying them separately, as well as we are creating a color composite image by using these three principal component images. Also displaying the explained variance ratio as well. In the final stage, we are displaying the principal component statistics, explained variance ratio in percentage format. Then we also displaying the cumulative variance explained. Now we have complete the code. Namely, we have see the code line by line. Before run this, I just summarized real quick. In the first step, I just imported necessary libraries. Second step, load the image. Third step, convert the image into RGB array. Then extract near infrared and red bands, because we are going to calculate the normal site vegetation index by using this near infrared and red bands. Then we just calculate the normal site vegetation index, named the NDBI image. Step 6, we initialize the scalar, namely min max scalar. In the step 7, we just created a dictionary object by using the original spot XS bandits along with the newly calculated this NDBI image, namely scaled NDBI image. By using this spot dictionary, we just created a spot data frame. By using this data frame, we just calculated the correlation coefficient between the features. Then we also plotted the scatter plots. Namely, we have here 16 scatter plots. We have here 16 correlation coefficients. Then in the step 9, we just initiate the principal component analysis, namely this PCA class, by passing the 3 output components. Then get the result. Namely, this is the PCA result. Namely, in this result, we have 3 principal components. Then step 10, we just get the explained ratio, and we just get the cumulative ratio. We explained it. And step 11, we display it the related spot XS bandits and the calculated NDBI image. Here we also display the results, namely result of principal component. Finally, we also display the principal component statistics. Now let's run the code and see the result, because we are here at calculating 16 correlation coefficient. We are displaying 16 scatter plots. Therefore, after we run, it takes some time. Now let's run this. First, we just get the correlation coefficients between the features. Namely, we have here 4 features. These are the correlation coefficients. And we have here maximum correlation coefficient, namely between the green band and the red band. In the previous lectures, we have seen that as a reference information. I just display it here. Namely, we have here 16 correlation coefficient between the 4 features. Then we just displayed the scatter plots. We just mentioned that we have 4 features here. Therefore, by using the scatter underscore matrix, namely from pandas, we can generate 16 scatter plots. The one thing is in the diagonal elements, they are not scatter plot, actually they are histograms. In the previous lectures we have seen that. Then green band between the red band, we have very high correlations. In the previous lecture we also seen that. Then here we have this is between the infrared and the green, because both has reflectance from the vegetation. Therefore we have a kind of scatter plot. We have here very high correlation coefficient between the green and this red. This is the near infrared, this is the green band, the red band, and the newly calculated NDVI, namely normalized difference vegetation index. In terms of this farmlands or this kind of hills vegetation, we have here very high value, but we have here a little bit low value, because near infrared is very sensitive to healthy vegetations. Therefore, we have very high value around farmlands. Then in this red band, we have less vegetation information. In the near infrared, we have high reflectance from the vegetation, but in the red, we have less reflectance from the vegetation. It's very clear from this image. Then we have calculated the NDVI, namely vegetation information. Let's see here, we have here very high vegetation information. It's corresponding to here. Now, these are the calculated principal components, namely the main results for this example here, namely principal components and the color composite image from the principal components. We have here three principal components. This is the first principal component, second principal component, and the third principal component. Here we have information. The first principal component occupies about 61.15% of the information. Namely, actually, we have here 4 images in the previous section. In the original data, about 61% of all information is concentrated or retained in the first principal component. This image newly generated from the principal component analysis, principal component result. Therefore, this is the most informative image or most informative image layer after the principal component. This is the second component, namely here we have 35.18% information inside this image. Then this is the third component. In the third component, we only have 3.51 information. Namely, if we cumulate all of this, it's about 99.85% image. Namely, previously we have 4 images, now we have 3 images as the result, and 99.85 image information are retained in these 3 images. Then finally, using these 3 images, I just created this color composite image, namely RGB image. In the R, I just assigned it the first component, namely R channel, red channel. I just assigned it the first principal component. In the green channel, assign it the second principal component. In the B channel, assign it the third principal component. As a result, we get this color composite image. Now let's see this image. We have all information, namely because in this 3 principal components, we have the 99.85% information retained in these 3 images. Therefore, I just created this RGB. Therefore, we have here different kinds of textures or different kinds of color here. Actually, we know that this area we have different kind of landscape. We have here farmlands, we have here actually natural forests, we have here riverbeds, water areas, namely river water, river bed, and these are the urban areas. We have here some kind of open or bare lands. Therefore, in this color composite image, we have different kinds of information, we have different kind of colors or textures. Therefore, the result of the principal component analysis is very good. Now let's see here in these images we don't have repeated or we don't have redundant images because these three images are independent, these three images are uncorrelated. In other words, these three images are orthogonal in terms of mathematically. Finally, I repeat again, therefore we have here 61%, 35%, and then finally we have here 3.1% image. These three images are independent and uncorrelated, as therefore we just created this RGB, namely color composite image. In this image we have all the information. This is the implementation of the principal component analysis. As a summary, we have implemented two results. In the first result, we just generated a kind of random data, then we created data frame. After that, we implement the principal component analysis. In the second example, we just used the spot XS image because in the real world scenario, sometimes we need to use image data as well. Therefore, I just used this. Principal component analysis is a very important technique and it's a very strong technique. Now, let's see the application of the principal component analysis. Until now, we have seen two examples. Now, let's see where we use principal component analysis. First, data visualization. Reducing high-dimensional data to 2 or 3 dimensions for plotting and exploring patterns. Namely, in the previous example, especially in the second example, previously we have 4 images, then we reduced it to 3 images, namely 3 dimensions. We reduced it. Then we just visualize it and see the color composite image. As that image, we have found that various kinds of patterns and different colors and different land cover types. Therefore, we use it for data visualization. Second, we use it for noise reduction, namely eliminating less significant components, namely low variances to clean data. In other words, the principal component analysis is a dimensional reduction, namely less significant components will be removed. Therefore, the principal component analysis will be used to noise reduction. Then, feature engineering. Actually creating new features from the principal components for use in machine learning. Namely, we have the original data, then we implement the principal component analysis, we generate the new 3 principal components. Actually, the newly generated principal component is different from the original features. Therefore, we can say this is a process of creating new feature. Then, compression. Reducing storage requirements by keeping only the most informative features. The previous example, we have seen that finally in the resultant 3 components, namely first, second, and third components, we have retained 99.85% in the previous example. This means that sometimes we only take the first 2 components. For example, if you have a data set with 10 numerical features and then we implement principal component analysis, and finally if we get first 3 components at that time, it's a kind of compression. Finally, preprocessing for machine learning models, namely simplifying data sets to improve model efficiency and reduce overfit. If you have a data set with 10 numerical features, sometimes features get overlapped information. If we use these 10 features in the model at that time, we encounter overfit. Therefore, first we apply the principal component analysis, reduce the dimensionality, and then we get the information, most of the information, and then we pass the data set to the machine learning models. At that time, we get the good results.